Okay. Now the third one. Any idea how to find that? I hope no questions in first two parts. If you have any question, you can ask. Even later, that's fine. Then we have to check whether x1 plus x2 is independent of x3. Remember to find whether two components, two vectors or scalars are independent. We have to have the joint distribution of those, right? Once we have the joint distribution, sorry. Let's see. Oops. Right. So once we have the joint distribution, we can look at the covariance part of the two components and check whether it's 0 or not. That's how we find out whether the two components are independent or not. Right. Now I'm asking whether x1 plus x2 is independent of x3. How can we find? So do we directly have the joint distribution of these two components? Do we have the joint distribution of x1 plus x2 and x3? Yes, Tarushi, your answer is correct. Answer or the question you are asking from me, yes. That's what we have to do. Yeah, that's what I'm trying to say here. So we don't have the distribution of x1 plus x2 with x3, right? So first we have to find the joint distribution of x1 plus x2 and x3. If we have this joint distribution, then we can check whether those two are independent, right? Because you have your variance coefficient. This is a 2 by 1 matrix now, or vector, 2 by 1 vector now. So you will have a 2 by 2 matrix here. So you can check whether sigma 1, 2 part equals 0. If so, it's independent, right? So what you have to do is first find the distribution of this one, x1 plus x2 with x3. How can we find the joint distribution of the two? Now you should see this as a linear combination, right? Actually speaking, these are two linear combinations. So to find the joint distribution of two linear combinations, we have to use the property 2, right? AX, that matrix. So not the total distribution, only the variance covariance matrix. We have to, yes, Ashoka, you have answered. Sorry, I didn't say. It's rule 2. Yeah, using the second property, we can find the joint distribution of these two. So you have to write this in AX form. That means you have to find A. First tell me what's A. Yes, Tarushi. And Daruni, it's really hard without seeing your faces. So either answer or ask, saying that you don't understand. Yes, I cannot figure out what's the thing going on. Yes, Pavanti, correct. Sevandi, yes, correct. Yes, Ivanga, correct. Did you understand what I just said? That we have to first find the joint distribution of these two to check whether those two components are independent or not, right? So then it's going to be a linear combination, two linear combinations. So we have to use the property 2 and find the variance covariance between these two components first. So I'm asking to find the variance covariance matrix. What's the A matrix here? That means this should be in the form of AX. So as I said, each row of A represent each linear combination. So yeah. Yes, Kasuni, yes, Nirasha, correct, right? So the first, yes, Nimasha, Tasneem, correct. Nimasha, only two linear combinations are there. We don't need a third row, right? So first linear combination, x1 plus x2. Second linear combination, simply x3. Just get me. That's my A, right? Now, what you have to do is find A sigma A transpose. Find A sigma A transpose. You have sigma, you have A, so you can find A sigma A transpose. It's a 2 by 2 matrix because we are finding the distribution of two linear combinations. So simply saying a 2 by 1 vector. So it's a 2 by 2 matrix, A sigma A transpose. Yes, Tarushi, correct. Yes, Himasha, correct. කොහොම පිරිමි ළමයි ටික දැන් ගෑනු ළමයි විතරනේ උත්තර දෙන්නේ වැඩි හරියක්. Yes, Pavanti. මම නම් කියව ගන්න හැටි වැරදිද දන්නේ නැහැ නේ. When there's an A at the end of your name, we can read it in both ways, as a girl or as a boy. Yes, Tarushi, that answer is correct. Yes, Nirasha. Yes, Dasita. I can just go ahead like without asking you, just write all these answers and I can just go on. But I want you also to, as I always say, learn something in class. Yes, Nadeem. Yes, Pavanti, those are independent, you are saying. Get Mini. Yes, get Mini, Nadeem. Tasneem. Nadeem. The variance value cannot be 0. One element is incorrect. Yes, Kalpani. I usually give you some time to calculate an answer. Yes, Sewandi. Yeah, Nadeem, now it's correct. I think the time is enough for those who answer. A sigma A transpose, it's 9002. Definitely full rank, right? A diagonal matrix, definitely full rank. Determinant not equal 0. So that means now we have to check actually x1, x2 independent of x3. Some of you have answered that part also. Yes, the covariance between the two is 0. Sigma 1, 2 part equals 0. That means these two are independent, right? That's independent. The first one is known, the other two independent, right? But remember, first two you can directly answer looking at the given covariance matrix. But for the third one, you have to find the covariance between the two first, right? After that, you can answer the question. Okay. Moving forward. So these properties are related. You can see the property 3 was there to partition our x vector into two parts, and we can get the distribution of each part separately. Then the fourth one said, if you have two parts with a multivariate normal distribution, then these two parts are independent if sigma 1, 2 part equals 0. So the fifth property says, if x1 and x2 are independent, now x1 and x2 are vectors, right? So it's better if I use brackets, right? X1, x2 are independent and distributed as mu1 sigma 1 1, mu2 sigma 2 2, right? Again, this one q by 1, q1 by 1, this one q2 by 1. Right. When we partition, we consider our p by 1 vector and partition into 2. But here in fourth and fifth properties, we are talking about two separate vectors, x1 and x2, x within parenthesis 1 and within parenthesis 2. So we take them as q1 by 1 and q2 by 1 because we are not talking about any p vector, p by 1 vector, right? So x1 and x2 are independent. These two components are independent. Now we have a special property, extra thing. Those two are independent and distributed as Q1 variate normal and Q2 variate normal respectively, right? Then this one is multivariate normal, x1, x2 within parentheses is multivariate normal with mean vector mu1, mu2. That means if you put these two vectors together, you can create a multivariate normal distribution with mean vector, the extended version, you just combine mu1 and mu2. And as the two are independent, you can see covariance part 0, but you have sigma 1 1 part from first part and sigma 2 2 part here, right? So you can create a multivariate normal distribution by putting these two separate multivariate normal vectors together, right? That's the fifth property. Right? So something that comes with something I explained last time, remember, according to the remark given after the first property. Here I explained last time that if you have a multivariate normal vector, then each of these x's are univariate normal, right? But if you have separate univariate normal ones, then by putting them together, if you create a multivariate normal vector, sorry, by putting them together, if you create a vector, that's not going to be multivariate normal, right? That was the remark. But you can see there's a small contradiction with that one. There's no contradiction. I mean, here in property 5, what we do is we have two separate multivariate normals, right? Q1 and X2. Q2. And we say by putting them together, we can create another multivariate normal. Yes, we can do that. Even here in the first one also, we can do this, and this becomes multivariate normal if that condition is there, if all the x's are independent, right? If these are independent, then we can put them together and create a multivariate normal vector, right? That same thing comes here in this property 5. Sorry. Yeah, in this property 5, same thing is there. If these two are independent, then by putting them together, we can create another multivariate normal vector, right? Remember that. So usually, if we have a multivariate normal vector, all components of it are going to be univariate normal. Not just univariate normal. If you break up like x1 and x2, according to property 3, you know that those parts also multivariate normal, right? Likewise, from a multivariate normal vector, we can get other multivariate normal or univariate normal components. But if we have separate multivariate normals or univariate normals, we can create another multivariate normal by putting them together only if those are independent, right? These components must be independent to have an overall multivariate vector. Is that clear? What this property 5 says and how that relates with the remark in property 1. So studying is not enough, right? Here, you have to think also. So think about it. All these properties are kind of related, right? We are talking about how to find the distribution of components in these multivariate normal vectors, right? We can create another multivariate normal, so we can partition original multivariate normal and get the separate distributions. Likewise, we can do a lot of things with these properties. Any questions so far? You can hear me clearly, right? Okay, thank you, Nandi. Okay, fine. Now, we are done with 5 properties, right? The properties we have looked at so far are about linear combinations of X's, right? We always talked about linear combinations so far, X's, partitions, or linear combinations, right? Other properties we discuss are about quadratic forms of X. Now, so we have four more properties. The last one is about the conditional distribution, but the other three properties we have next are going to be about quadratic forms of X's, not linear combinations, right? So far we considered linear combinations like x1 minus x2 plus x3, likewise. But if you have like square terms, x1 squares, x1, x2 terms, or x3 squares, likewise. If we have a quadratic form, how to find the distribution of those? Okay, first of all, definition of quadratic forms. Let a P by P symmetric matrix. Let A be a P by P symmetric matrix. Let QX be of the form. That means a function of X's, right? A be a P by P symmetric matrix. It is a separate matrix. X. This X is our usual P by 1X. So a function of X. So far we had functions of X. We'll say fx, these linear combinations. Now we are talking about quadratic equations, QX type ones, right? So X transpose AX. That means this form, summation ij, aij, xi, xj. So any xi, xj, any combination of x's, right? So then QX is said to be, that means this one, you're something like this, right? An example, you have in notation like summation I goes from 1 to p, j goes from 1 to p, aij, xi, xj, right? So it's like a1 here is simply 1. So xi, xj, both I and j equals 1. Then you have simply x1 square, right? Here a12 is 2. I equals 1, j equals 2, right? In notation, we can write a quadratic form in this form. Then QX is said to be a quadratic form in the P variables x1 through xp. And here are some examples, right? So if the quadratic form is x1 square plus 2x1 x2 plus x2 square. So we have only two responses there, x1, x2. You can write this in this form, in X transpose AX form. So definitely X is x1, x2. You will have a matrix here, A matrix, P by P matrix, and x2, sorry, X transpose C, right? So what's the dimension of the matrix A now? This is my A. Dimension of A should be yes, Himasha. Yes, Tarushi. Nadeem, according to this particular example, I'm asking the dimension of A. Yes, generally A is P by P, but I'm considering this x1 square plus 2x1, x2 plus x2 square, this particular example. Yes, Dasita, yes, Shashika, Tasneem, Kalpani, Nirasha, Avanti. Yes, right. It's going to be a 2 by 2 matrix. Now remember, it's easier to write this matrix if you know the way, right? The first element, very first element should be the coefficient of square. Anywhere along the diagonal, you have the coefficient of square terms. So the first diagonal element should be the coefficient of x1 square, which is 1 here, right? So this would be 1. Now the second diagonal element should be the coefficient of x2 square. That's also plus 1. Right? Then the off-diagonal elements, you can get x1, x2 coefficient divided by 2. Right? You have to always divide the x1, x2 coefficient by 2 to get the value here. So it's positive 2, the coefficient. So this should be also 1. Right? So if you multiply these three, you can get this one, x1 square plus 2x1, x2 plus x2 square. You can calculate and see. Try to multiply this. So you have to first multiply x1, x2 with 1, 1, 1, 1, that matrix. So you will get x1 plus x2. Then again x1 plus x2. Then you have to multiply that again by x1, x2. Just find it and see whether you can get that exact quadratic form. Were you able to get it? So you can get x1 plus x2 times x1. So x1 square plus x1, x2 plus x1, x2 plus x2 square. So from this one, x1 square plus 2x1, x2 plus x2 square. Right. So you can always get the quadratic form using that method. Along the diagonal, you have the coefficients of square terms, and off diagonal elements are the interaction terms, x1, x2, x2, x3, likewise. Divide by 2. And the matrix is always symmetric. Remember that also. Now, the next one, qx equals x1 square, x1, x2, x2 square, x2, x3, x3 square. So you can see clearly x is a 3 by 1 vector there. So we'll have x1, x2, x3. We'll have the matrix A, and again x1, x2, x3. What's the dimension of matrix A here? For this particular example, what's the dimension of A? Yes, Pavanti. Yes, Tarushi. Yes, Sevandi. Yes, Tasneem, Dasita. Yes, it's going to be a 3 by 3 matrix. Now, again, along the diagonal, those are the coefficients of square terms. So the first element is x1 square coefficient 1. The second diagonal element, x2 square coefficient, which is -1. Third element, x3 square coefficient, which is 2. Right? What do you think that comes here? the second element in the first row. Nadim, remember we have to divide by 2. The coefficient divide by 2 always. The off diagonal elements, right? Yes, Ashoka. What's that calculation? X1, X2, half X1. Yes, I'm asking for a particular, yes, Tarushi. That's the one, but I'm just asking for this particular example. What's the number comes there? Yes, Pavanti, yes, yes, Tarushi, you have answered later. Yes, Vibanga. Vibanga or Vibanga? Ga. I don't know. Either way. Yes, that's the x1, x2 coefficient divided by 2. So 6 divided by 2, it should be 3 here. What's here? Third element of first row. Yes, Tarushi, yes, Pavanti. It should be the coefficient of x1, x3 divided by 2. So x1, x3 term is not there. This should be 0. Yes, Ashoka. Then this element. That's the x2, x3 coefficient divided by 2. So minus 4 divided by 2, minus 2. It's a symmetric matrix. So here it's 3, here 0, here minus 2. That's the A matrix. Now I'm going to ask a question. Can this matrix A be a variance covariance matrix? What do you think? With the things you know about a variance covariance matrix, I am asking, can this matrix A be a variance covariance matrix? Yes, Ashoka, exactly. Yes, Dasita. Yes, correct. Good. Vibanga, Nadim, take a better look. Others, neither. Yeah, the 24 අම්මෝ 24යි 51. Not even half the class. I don't think I ever had like that in a multivariate lecture. This honors degree lecture. Poor attendance. I don't know the reason. Anyway, only 4 answered. Others? What do you think? I'm just asking, looking at this matrix A, can you think whether this can be a variance covariance matrix or not? Yes, Nirasha. Why? If you say no, there should be a reason. Yes, exactly. Yes, Nirasha, correct. Pahai, 24 උත්තරාවේ. වීඩියෝස් ටික ඔන් කරලා බලමු ද ළමයි ටික ඉන්නවද කියලා. දැන් දුවයි දන්නේ කට්ටිය හොම් කිව්වහම කොහොමද? ඕන්නේ. If it goes this way, my enthusiasm also goes down. You know, that happens. When I see poor attendance, no answers for questions. So there are like some of you answer, I know. That's good. But overall in class, it's poor. Yes, Tasneem, correct. ළමයි ට්‍රිප් ගිහින්ද දන්නේ නැහනේ නිවාඩු අල්ලලා. හෙට්ටයි අනිද්දායිත් එක්ක නිවාඩුනේ. Do you have lectures tomorrow or day after? Probably not day after, tomorrow. Still, I don't think, right? Those are public holidays. That may be the reason for poor attendance. It's Monday and Tuesday and Wednesday holiday. Not an excuse at all, but yeah, that may be a reason. Otherwise, I have never seen this much of poor attendance. So the best thing is I have to give some quizzes or something in class unannounced and take them for grades. That would be a good option. We'll see. Okay, so this one, the question I asked, yeah, few of you answered correctly. Yes, it cannot be a variance covariance matrix because along the diagonal you have a negative value. So in the negative, there's a negative value along the diagonal means, or in a diagonal element you have a negative value. That means that's a variance value. A variance value can never be negative, right? Variances are always positive. So if you have negative values in the diagonal, that means it's not a variance covariance matrix. Okay. Did I have the correct? Yeah, these are not actually omitted. These are exercise. You are honors degree students. Mistakes. I don't know how come it became omit. The applied multivariate I usually omit these, but these you should know. Okay, so as I said, next three properties are based on these quadratic forms of x's. Now, we have three properties here. The sixth property, the first one from quadratic forms. If C is distributed as p-variate normal 0, I. So far, okay, first of all, what's the dimension of Z? Looking at this multivariate normal distribution, you can easily say what's the dimension of Z. Yes, Himasha. Yes, Pavanti. Yes, Tarushi. Yes, Dasita. Sevandi, get mini. Yes. Yes, it's a p by 1 vector, right? Otherwise, it cannot be p variate. So Z is p by 1. So far we always used X, but here I have used Z. Why? Any idea why? In univariate also, when you talk about the distribution, normal distribution, sorry. Univariate also, when you talk about normal distribution, you always use X. But there's a situation we use Z. When? If it's normal, 0, 1, right? That means if it's standard normal distribution. So here also Z is used here because it's the standard normal version of the multivariate normality also, because the mean is 0 vector and variance covariance is I identity matrix. So you can see that's the standard form. So it says then Z prime Z, that's the quadratic form, right? If Z is a P by 1 vector, then Z prime Z, it's going to be, okay, what's the dimension of Z prime Z? Yes, Pavanti. Yes, Dasita. Yes, Nadeem, Himasha. Yes, right. It's a scalar. So quadratic form, same as a linear combination. X is a vector, but any linear combination of x's, it's going to be a scalar. Scalar means actually a random variable, right? Because you use scalar, the word scalar before. If you have just kind of constants also, but here those are random variables, but scalar means just 1 by 1, right? In multivariate, when we say scalar, it's 1 by 1 random variable usually. So Z prime C, it's a quadratic form, right? Here these quadratic forms, again those are 1 by 1, right? If we have a quadratic form, that's again 1 by 1. So Z prime Z, it's 1 by 1. That means it's a univariate distribution. And it says it has a chi-square P distribution, right? If Z is standard normal 0, I, then Z prime C has a chi-square P distribution, right? So we have to prove this. Proof we are going to do, we'll have a small break. Otherwise, every time the break was dragged to the latter part. So we'll have a small break of about 10 minutes and it's 10:59. We'll start at 11:10, right? Okay. If you have any questions, you can ask for that.